schedule and can uplift his presentation now. Is it possible, madam?
If the next speaker, who is the next speaker?
The next speaker is Ranjana Goswami.
Is she present?
Are you present, madam? Ranjana, madam, are you present? I
If the
can't
next speaker
see her
is not
name.
present, then we can allow Sanghamitra Sanyal to present his.
Okay, madam. I can't see Ranjana Goswami's name in the people
Yes,
list.
then we can
Okay.
allow him on her place.
So I will invite Mr. Sanghamitra Sanyal to discuss making sense of matrix comparing 6 water quality assessment techniques. Sir, please.
Thank you. Let me just share that slide first. Uh, can you see the presentation?
Yes, sir. Your presentation is visible.
Good afternoon, everybody. Esteemed professors, fellow scholars, and other seekers of knowledge. Today, my topic is making sense of metrics, comparing 6 water quality indices. I'll jump into the gist of it. The basic idea, as has been discussed before in this very day, that water is basically of vital importance to us, and it is fresh water. The availability of fresh water is becoming less and less every day, and that is actual threat to our existence. Now, to measure the quality of water, one of the most important methods which is used is called the water quality indices. WQI, that is water quality index. And sadly, there is not one water quality index that is used world over. As you can see from the image out here, there are numerous water quality indexes that are used all over the world. Actually, there are quite a few that are used in India itself. The basic idea of water quality indices, if I can just, if you discussing very short, the basic idea is there are various different water quality parameters. We can have physico-chemical water quality parameters. We can have biological water quality parameters, etc. And the idea is we combine the knowledge from all of this into a single number, and that number is basically our water quality index. How do we do this? Depends upon the water quality index that we are discussing. The first of its kind was actually devised by Brown in around 1960s, and from there on, a lot of different people have devised or basically come up with different water quality measurements, including biological parameters, which are there, and use various different statistical techniques, high dimensional techniques, etc., to come up with this water quality index. Now, my work out here is I have chosen basically 6 water quality indices which are popularly used in India or developed in India for Indian rivers. WAWQI, which is basically a very generic one, which is very similar to what Brown had developed. OIP is overall index of pollution. STWQI is Swami Tyagi water quality index. RGWQI, also called the CPCB, that is Central Pollution Control Board, CPCB WQI. This is River Ganga water quality index. OWQI, this is the overall water quality index, and CWQI is comprehensive water quality index. Both developed by Surjit et al. One in 2015 and then 2018. So these are the latest techniques that have been developed. Now I have two sets of data. One is a simulated data set. The simulated data set, what I have done is basically say I have with these various parameters. So I have these I have these various parameters, say x1, x2, x3, x4, etc. So for the first 100 data columns, what I have done is basically I have varied these data randomly between their minimum value and their maximum value according to IS 10500, that is the drinking water quality standards of India. Wherever basically these standards were not available, I used either standards from United Nations or EP, etc. And then starting from then, the next say 100 data sets, one of the variables started off from the max value and then continued to with every step basically increased by 10%, so that basically in the 100th reading it is twice the max value, while the others basically were randomly varied between their minimum and maximum value. After that, this one carried on similar to these. The second one now started from its max value and then went out to 2 max value, twice its max value by increment of 10%, so on and so forth, for all the different values. Okay. So what this gave me is basically a data set with more than 3,800 samples. And for each of these, basically, I calculated the water quality index, WWQI, OIP, STWQI, RGWQI, OWQI, and CWQI. And then they were analyzed by using techniques like ANOVA, 2KHSD, PCA, random forest, etc., to find out what were the basically how they reported the water quality, how each of these basically reported the same kind of water quality on the simulated data. Once this was done, what I actually found was, I'll show it to you later, that what happens is uh, they are not all reporting the same results. Because of this, I had to develop basically another data, which was another water quality index, which was basically a PCA average of these. I then used the same simulated data set and compared the PCA average the water quality index with these six. And once I was satisfied, then we used real data from Damodar River, real data from Damodar River from 2014 to 2024. Monthly data was available from the West Bengal Pollution Control Board website. And basically, they were also analyzed to see whether these water quality indices are all behaving the same way, uh, like it behaved with the simulated data. The sample sites, according to West Bengal Pollution Control Board, they start from here, S1, that is Borakar. Then we have Dishergarh, Damodar Bridge, Riverside, Raniganj Mijia Bridge, Vallabhpur, Madanpur, Pursha, Damodar Barrage, and finally Majarmana village. This is basically about downstream of the Damodar Barrage, around 1 or 2 kilometers downstream. So this basically covers the entire gamut of Paschim Bardhaman. This is a summary of the different water quality indexes. This part, whoever basically proposed this, I have already told you. The criteria of calculating these are mostly, for example, WFI is a weighted arithmetic mean based on parameter subindices. That is, every parameter was assigned as a subindex value, usually from expert opinions or some mathematical formula. And there were 9 parameters that were used here. So all available parameters were not used for each of these indices. Overall index of pollution, this was basically developed by Sargaonkar and Deshpande. They work for NIRI. They used 10 parameters. Swami and Tyagi, they use geometric mean of quality ratings using weights. They use 12 parameters. River Ganga, Ved Prakash basically developed it for CPCB. This is very similar to WQI or actually NSFWQI. They simply use 5 parameters. So this is one of the simplest. OWQI developed by Singh et al. Average of normalized scores weighted for Indian context. Please do not mistake this for Oregon Water Quality Index. Uh, they use 15 parameters, and then CWQI. This is the composite scoring, composite water quality index. So basically, they use actually even more, which is similar to OWQI, but they actually refined their method and actually included almost 25 different parameters which were available from the CPCB websites. Now, one problem that we come across, this is water quality indices, the categories, that is what is good quality water, what is bad quality water. They don't basically have the same scale. For example, if you see WAWQI, 0 to 25, the value of when WQI value lies between 0 and 25, it's an excellent quality water. And as the value increases above 100, it becomes unsuitable. That is, the water is completely unsuitable for drinking. River Ganga actually goes the other way. Here, 63 to 100 is basically excellent quality water, and below 24 is unsuitable. So these are two scales going in opposite directions. Overall index of pollution, again, it basically rises. The lowest value is excellent, and the highest value is unsuitable. Swami Tyagi the water quality index. This is again similar to River Ganga water quality index. That is, the higher values are actually the range lies between 0 and 1, and the higher values are actually for excellent water quality, and the lower values are for unsuitable water quality. CWQI and OWQI, again, higher values are basically for excellent water quality, and lower values are basically for poorer water qualities. But if you see the scales, they are slightly different. For OWQI, it is 0 to 24, while for CWQI, that is 0 to 25. So just value difference of 1, and suddenly in one scale you are unsuitable, and the other scale you are just very poor. So what I propose is basically rescaling all of these before we compare them into a single scale which ranges from 0 to 5. This is basically, I picked 0 to 5, that is basically a very popular choice in various different scaling methods. So 0 to 1 is unsuitable, 1 to 2 is very poor, 2 to 3 is poor, 3 to 4 is good, and 4 to 5 is excellent. Any value basically goes higher than 5 will cap it at 5. Any value which goes below 0 will cap it at 0. Now, if you look at the simulated data, remember this data is basically which is completely generated by computer, and even there, none of these basically indices they agree with each other. Where water WAWQI is basically giving us, remember what 4 was basically good quality water. Okay, OIP is basically saying that the water quality actually ranges 3 to 4, that is poor, or rather it's basically 2 between around 3, so it's between 3 to 4, so that's poor. Swami Tyagi says that this is basically between 0 to 1, that is completely unsuitable. River Ganga water quality index says that it is very good quality, and OWQI and CWQI kind of agree with it. I'll come to this last one, that is PC mean, a little later. Okay. So what we did is basically we took all these data and basically all the simulated data, and we basically did a PCA on it. And on PCA, if you look at this is basically called a scree plot, and it is supposed to reduce the number of dimensions. So I had around 35 different variables, independent variables. I was supposed to reduce it down to 1 or 2 variables. But if you look out here, the first 2 components explain barely 15% of the data. So this data is multidimensional in nature. Okay, the first 2 components barely, I mean, generally, if you want to do basically reduce the components, the first 2 components, if they explain at least 75% variation in the data, then PCA mostly is useful. But for the first 10 components, basically doesn't cover all that. If we basically look into the biplot, please notice, remember, the horizontal one basically is where you see the maximum variation, and the vertical line is basically you see the second most variation. And if you see out here, uh, STWQI and OWQI are basically kind of grouped up with fluoride. So basically, their variation is mostly due to fluoride. OIP, RGWQI, and WAWQI, they are basically mostly due to physicochemical factors. Okay, and that is basically physical factors. Okay, like conductivity, total hardness, turbidity, temperature. Okay, and CWKI is mostly affected by organic factors like coliform, etc., and nitrogen, and PCAWQI, that is the one which we generated. This is strongly affected by coliform and silver. If you want to see this basically like this, if you see these are the top five loadings. The ones in orange are basically the water quality indices, and the ones in blue are basically the water quality parameters. To see this lightly better, basically to find trying to find out which variable or which independent variable actually affected our water quality indices the most. I did a random forest this thing, what do you call, multiple regression analysis. Okay, where each of these basically the water quality parameters were the independent variables, and the water quality indices were the dependent variables. And if you notice out here, for CWQI, it is basically explained mostly by silver. Okay, the highest variable basically variability is shown by silver, followed by fluoride, cyanide, iron, and selenium. For OIP, it was total coliform, then hardness, pH, DO, and chloride. For OWKI, it is total chloriform, nitrogen, fluoride, arsenic, and then iron. For RGWKI, that is total chloriform, pH, DO, temperature, and BOD. So if you notice, basically these are slightly similar. STWKI, nitrate, fluoride, pH, DO, TDS. So you see there is some variables that are basically being repeated in all of these. Okay. And WAWKI again total chloriform, phosphate, pH, DO, BOD. So pH, DO, BOD basically figures in almost most of these along with nitrate, nitrogen, fluoride, arsenic, etc. And PCAWQI basically has kind of integrated all of these except maybe silver, which is present only in CWQI, but basically it is being affected so strongly that it is figured in here as well. But other than that, if you notice, it is affected strongly by total chloriform, nitrate, and phosphate, and pH. These are basically the top five important variables, not all the important variables. Uh, if you want to see how all these independent variables basically kind of vary with the individual water quality indices, basically this is the graph. The intense red color basically shows a strong positive correlation. The deep blue color shows a strong negative correlation. So as you can see, there are very few strong positive or negative correlations. Other than maybe for STWQI, the fluoride shows a very strong positive correlation, and for WAWQI, total coliform basically shows a strong negative correlation. So there are some of these. For CWQI, again, silver shows a strong positive negative correlation, whereas PCAWQI shows a strong negative correlation. Uh, Once this was done, we moved on to basically the real data. For real data, if you see, this is basically variation by months. So this is basically from January to December. These are variations of all these water quality techniques by month. As you can see, the pattern is very similar. Uh, uh, for real data, actually, water quality WAWKI is actually showing poorer quality, whereas basically overall index of pollution and the others are actually showing better quality. So water quality index is actually showing poorer. And if you see out here, cumulative STWQI, this is another one which is basically showing poor value. Okay. If we do the box plot by station codes, that is the 10 stations specifically we had out there. Again, you will notice poorer quality for WAWQI and STWQI, and much better results for OIP, CWQI, OWQI, and RGWQI. On performing PCA, again you can notice that this is the even the real data is also very extremely multidimensional, and even after taking 10 principal components, only 64.6% of the variation has been explained. A biplot, the dots out here are basically the just various different water quality indices, water quality values, and these arrows basically show how they are behaving with respect to each other. I have not centered this plot. So if you see water WWKI, OIP, HGWK, and PCAWKI, they are all basically grouping together, and RGWKI, OWKI, and CWQI are basically behaving differently. So overall, basically we can conclude that number one, both types of data have extremely high dimensional. In the principal components, the principal component one is mostly about ionic or mineral content. Principal component two is mostly about microbial and heavy metals, microbial data and heavy metals. The biplot shows basically clustering bit where basically WWKI, OIP, and STWKI clustered together with principal component 2 that basically is mostly about pollution. CWK and OWK are basically aligning with principal component 2 in the negative way. Basically, it's aligning strongly with hardness. This is basically the correlation of the dependent and independent variables for the real data. And you can see out here there are pretty strong positive and negative correlations out here. Okay. A cluster heat map of the WKI data from the real data. You can see out here again. There are two major groups. One group is basically OIP, WWKI, PCAWK, and STWQI. And the other group basically contains CWQI, OWQI, and RGWQI. This is very similar to what we have seen already in PCA. And even between them, it is OIP and WWQI which are basically clustering together. And then basically we have a branch of PCAWQI. So PCAWQI is basically taking some information from STWQI, WWQI, OIP. Mostly it is being influenced by these, and it is being less influenced by CWQI, OWQI, and RGWQI. And PCAWQI, what I actually did is basically I took all these water indices that was scaled from the range of 0 to 5, and then I scaled it again, and from basically like
Sir,
what you do.
sir,
Yeah.
sorry to interrupt, but please conclude. Your time is already up. Please.
Okay, just give me 2 minutes. I'm done. And then I basically, based on the loadings of basically the values of loading first principal component 1 loadings, I basically calculated it. This is the plot. This is basically the line plot, or basically the time series plot for all the different water quality indices in their own scales. And this is basically in the common scale. Okay. Importance: PCAWK reflects combined behavior of all the 6 water quality indices. Random Forest identified total coliform, lead, iron, fluoride as key predictors. It balances extreme sensitivities and aligns with real data trends. Interpretations and policy implications: water qualities are not interchangeable and can conflict in classification. Risk of miscommunication in regulatory reporting thus becomes very high. PCAWK provides harmonized outputs with policy alignment and enables better informed decisions for water safety and planning. Conclusions and future work: water quality shows significant difference in behavior and sensitivity, even for same water data. PCAWQI offers a robust composite evaluation of water quality, and future work I want to test it out on more real data which becomes available to me and integrate this with spatial mapping and remote sensing data. That's it for today. Thank you.
Thank you, sir. I don't think there is any time for any question. Is there anything? If not, then I will move to the